In this video, we're going to talk about the sum function. So recall that in section 3.2, we defined a finite series as the sum of the terms of a sequence. And we saw that the sequence could actually be defined recursively. So if we have the sum from 1 to n of some a sub I, we can essentially break that up as the sum from 1 to n minus 1, and then tack on that extra final term of a sub n. So let's give a recursive definition for a sum function to prove that our function works, to essentially prove that we can do this. So let L be a list of real numbers. So we're going to let our set of things we can pull from be the real numbers. And we're going to define the function sum of that list in the following way. Essentially, the base case is going to be if L is x, so just a single number, then the sum of L is just going to be x. Now, if L is some smaller list with a final term of x for some list L prime, then the sum of L is going to be the sum of L prime plus x. So notice in this definition that the input to the sum function is a list of real numbers. And remember that a list can be one thing. So let's see how this would actually work if we wanted to actually use it. Now again, this is another one that seems very obvious to us because we've essentially already used this so much in our lives. We know how to add numbers pretty easily, but if we think about breaking it down into its very basic steps, and if you think about trying to program something into a computer, you often do have to break it down into very basic steps. So if we think about how to use this function, so we're going to use the definition of the sum function to add the numbers in the list 7, 2, 5, and 9. So again, we are very used to adding numbers. We can add those numbers together very well, but how can we actually do it using this sum function? So we have a list 7, 2, 5, 9. And so if we plug that into the sum function, we're already starting with a list. So essentially we have to start with that recursive step that says essentially take the smaller list, essentially everything but that last term, so the 7, 2, and 9. And that's just going to get written in another sum function again. So sum of 7, 2, and 5, and then we're just going to add on plus 9 at the end. So this would be a recursive step in the definition we just kind of scrolled past. And then if we do it again, well, again, we have a list now. So the list we have inside that sum function now is 7, 2, 5. So we take the smaller list, everything but the last term. It's going to stay in a sum function. We're going to have plus 5 at the end, and the plus 9, of course, still kind of tags along. Well, now we have a list 7, 2, and so our recursive definition says essentially take everything but that last term and keep it in a sum function. So sum of 7, and then the plus 2 essentially comes out, and then the plus 5 and plus 9, of course, kind of just come along. At this point, we get down to the sum of 7. Now this goes essentially to the base case, where it's just one number. So since it's a list of just one number, the sum of 7 is just defined to be 7, and then the plus 2, plus 5, and plus 9 kind of come down. So that was a base case step. And then, of course, if we actually add these all together, we get 23. Now again, we've been adding things almost all of our lives, so this might seem a little simple. But what we want to think about here is that we were able to define this function to be able to find the sum of any string of numbers, even if, whatever program we put this into, maybe it doesn't know how to add numbers like we do. But it can take this function and now say, here's a string of numbers. Oh, I know how to add them together now. So when we evaluate a recursive function, we call this function again and again by the recursive step until we're able to evaluate the function using the base step. So that's essentially what happened here. We had to call upon the recursive step 3 times before we could use the base case and then actually put them all together. So let's actually prove that this function works. So say we want to show that for any list of n real numbers, so x sub 1 through x sub n, for n greater than or equal to 1, that the sum function is going to return x sub 1 plus x sub 2 plus onward and onward plus x sub n. So let's actually prove that this function does what we say it does. And we're going to have to prove this by induction. So we have to start with our base case. So that's going to be on n equals 1. So essentially we need to show that sum of x sub 1 equals x sub 1. Well, that's actually just by definition, by the base case of the definition. So by the base case of the definition. Because if you think about what this would turn out to be in essentially the series way, the sum way, we would just have x sub 1 plus nothing else because all we have is x sub 1. So sum of x sub 1 is equal to x sub 1. We're good in that case. So now we have to write down the inductive hypothesis. So we're going to assume that it's true for some k minus 1. So we're going to assume, let's start with assuming k is greater than 1. So we're going to assume that k is greater than 1 and that the sum, let's go ahead and call it L prime, is equal to x sub 1 plus x sub 2 all the way up to adding x sub k minus 1 for any list L prime on k minus 1 numbers. Now the reason I'm using L prime and not just L is just because it's going to make the notation in the next step easier. I'm not going to have multiple L's floating around because I really shouldn't have two things named L being different things. So I would have had to name the other L in the next step something different anyway. So let's just go ahead and make this, technically smaller list since we want to increase to k numbers instead of k minus 1. Let's go ahead and make the smaller list L prime, sorry. So now we're on to the inductive step. So we essentially want to look at this statement for k. So we essentially want to show that the sum on L equals x sub 1 plus x sub 2 all the way up to x sub k for any list L on k numbers. So again, just a reminder of kind of what we're shooting for. We don't have to write that down in an official proof. But so essentially we want to start with sum of L and try to work over to the right side. You don't want to start by setting these equal and try to go down on both sides. Start with one side and work towards the other. So let's go ahead and start with sum of L. So let's go ahead and say let L, let's be a bit more official here. So let's say let L be a list of k numbers, sorry. So we'll say that L equals x sub 1, x sub 2, all the way up to x sub k. So we're going to have sum of L is equal to sum of L prime plus x sub k by the recursive definition. And that's because, so by the recursive definition, as L essentially equals L prime comma x sub k. Because essentially L prime was essentially the list x sub 1 through x sub k minus 1. So if we're just tacking on an extra x sub k at the end, we can then view the list L as the list L prime comma x sub k. So by the recursive definition, that's how the sum function is essentially defined to work. Well, now what is sum of L prime? Well, we know what that is by the inductive hypothesis. So we can essentially say, thus, this sum of L prime plus x sub k is equal to x sub 1 plus x sub 2 plus all the way up to x sub k minus 1 plus x sub k by the inductive hypothesis. Because essentially this sum of L prime is this x sub 1 added together all the way up through x sub k because we said so in the inductive hypothesis. So just highlighting where that replacement is coming from. So now that we've essentially finished our inductive proof, we should just write out kind of the final statement. So we should say, by induction, sum of L equals x sub 1 plus x sub 2 plus all the way up to x sub n. So let's switch back to n's now for our final statement. So this is going to be true for any list of n numbers, where n is greater than or equal to 1. Because remember, the equal to 1 case we take care of in the base case, and the greater than 1 case we take care of in the inductive hypothesis to the inductive step. So we've now essentially proven that this sum function works exactly how we think it should. So this is where we're going to end this video. In the next video, we're going to talk about this type of recursive data structure in terms of binary trees.